What are you doing, William?
Oh, I'm making a paper airplane.
Really?
Yeah.
Interesting. Well, let me see it fly.
Let's see how it flies.
William, what are you doing?
I'm trying to make
That's such a terribly designed airplane.
Tell
It
me why
has
it's
no wing
terribly
area
designed.
at all. No wing area, and the drag force is huge.
That's very unfortunate. So I'm bad at making paper airplanes?
Exactly. We need to teach you some things.
Okay. Drag is the force of friction between an object and the surrounding fluid, which always acts in the direction opposite the object's velocity. Some examples of this would be like a textbook. A textbook is not very aerodynamic and its drag coefficient is very high, while on the other hand, an airplane is, I would say, fairly aerodynamic and has a low drag coefficient.
Drag force is equal to 1/2 times c sub d times rho times a times v squared, where c sub d is the coefficient of drag, rho is the density of the surrounding fluid, a is the cross-sectional area of the object, and v is the velocity that the object is moving. As you can see, the velocity has a greater influence on the overall drag force than any other component inside the formula.
So, the plane that William made was very bad in terms of drag because it had a very blunt nose, which led to it having a very high drag coefficient. And also, you can see that this cross-sectional area in front is very high. It's not, streamlined. So, that meant that it lost its velocity very, very quickly because that force acted in the reverse direction from the velocity. And so when you tried to throw it, it just flew straight to the ground because it lost all its velocity almost immediately.
Lift is the force that holds an airplane in the air, counteracting the force of gravity by creating a pressure differential across the wings of a moving airplane. This pressure differential can be explained through something called Bernoulli's principle, which states that the sum of the pressure, kinetic energy, and potential energy across all parts of the wing are going to be the same. Therefore, if the velocity across one part of the wing is higher than the velocity across another part of the wing, then the pressure where the velocity is higher will be lower, and the pressure where the velocity is lower will be higher. Therefore, you have a situation where there is high pressure on the bottom of the wing and low pressure on the bottom of the wing, which causes it to go upwards.
We see that the formula for lift is very similar to the formula for drag. Only two values are different. The first is the coefficient used. Here, a coefficient of lift is used in which it is determined by the angle of inclination of the airplane as well as the type of airfoil being used. The second is the area calculation. So in the drag force calculation, the area used was the cross-sectional area of the plane. However, in the lift calculation, the overall area of the planes are used.
Williams' airplane also had very poor lift characteristics due to its extremely small wing area and also asymmetric lift. As you can see, one wing is slightly larger than the other. So this, combined with the slow velocity from earlier, meant that it produced very little lift and therefore, dropped to the ground very quickly, did not really glide at all.
So William, what did we learn? What are the best characteristics that we want inside of your airplane?
So we learned that we need to decrease drag, and we can do that by decreasing the cross-sectional area of the front of the plane by making the front of the plane pointy. We also learned that we want to increase lift, so we need to make the wings bigger. Instead of making them really small and narrow, we need them to be long and wide.
So can you apply that to what we have here in front of us?
We'll see. In this example problem, a hypothetical airplane has a coefficient of lift of 0.63 and a drag coefficient of 0.50. The airplane weighs 19,000 kilograms with a wing area of 550 square meters and a cross-sectional area of 68 square meters. The density of the surrounding air is 0.147 kilograms per meters cubed, and if the turbines are exerting an overall thrust force of 20,000 newtons at 86 meters per second, what is the magnitude of the overall net force exerted on the airplane in what direction?
Okay, so we're going to begin this problem by drawing a free body diagram real fast. So we have our force of lift, the force of thrust, the force of gravity, and the force due to drag. So they give us the force of thrust as 20,000 newtons. We can calculate force of gravity as being equal to mg, which is equal to 19,000 kilograms times 9.8 meters per second squared. So if I calculate that real fast, that comes out to 186,200 newtons of gravitational force. So we're going to counteract that gravitational force with the force of lift, and the force of lift is going to be equal to 1/2 times the coefficient of lift times rho times the area times the velocity squared. So if I'm going to go ahead and plug that in, we have the coefficient of lift given as 0.63, rho is given as 0.147, area was given for the lift component as 515 meters squared, and the velocity was 86 meters per second. So as I go ahead and plug that in, 0.63, 147, 550, and 86 squared. I'm going to get 188,359, and that's going to be newtons. Okay, and then I can go ahead and then subtract those to get the overall force in the y direction. So the net force is going to be equal to that force minus that force. So if I go ahead and just do that subtraction on my calculator real fast, I'm going to go ahead and get around 2,000 newtons of force. And then I can go ahead and, well actually it's going to ask for net force, so I'll leave that there for now. Now let's go ahead and do the drag force. So they gave us thrust force at 20,000. So drag force is going to be equal to 1/2 times the coefficient of drag times density and area and velocity squared. Go ahead and plug those numbers in. The area will be different, the coefficient of drag will be different, but otherwise it's more or less the same equation. So 0.5 times 0.5 times 0.147 times the area is now 68 for the cross-sectional, and then velocity is still 86, and we're going to square that velocity. So that gives us 18,482. These are newtons. And then that's a little bit less than our 20,000 value for the force of thrust. So we'll go ahead and find a net force in the x direction, and that's going to be around 1,500 newtons. Okay, so we have now our net force in the y and the x direction. To get the total magnitude of overall net force, we're going to go ahead and just use the Pythagorean theorem. So I'll take the square root of 2159 newtons squared plus 15 newtons squared, and that's going to equal the square root of 2159 squared plus 1517 squared.
Then remember to square both sides, or square both values.
Yeah, I am, right?
Pythagorean theorem.
Yeah, 2159 squared and 1517 squared.
Okay.
Okay, perfect. 2638, and that's going to be newtons. Okay, so that's the overall force on the aircraft. Now, because the force in the y direction and the x direction were both positive, that means that the aircraft is going to be moving in this direction, forward and upward, which means that it's climbing. And if we want to, we can go ahead and divide that force by our mass again. And then that's going to yield the total acceleration on the aircraft, which comes out to be around 1.3 meters per second squared, which is about what you would experience in a typical airplane takeoff.
Awesome, I see that you're maximizing the wing area.
So you'll notice that there is no longer a blunt front to this. You'll notice that the cross-sectional area is very small, and these wings are in fact rather large. Let us see it fly. I learned about the properties of lift and drag.
So can you apply them right now?
I think I can.
Awesome.
Into this cool paper airplane.
Let's see.
I'm done for the day, actually.
William, for designing such a horrible plane earlier,
You now face execution.
Oh no.